This is problem 1-3. Note on this problem here, and especially if you ever have a test problem like this, make sure you note whether or not the beam itself has weight. This one has 80 pounds per feet. So 80 times 3, that's 2,400. So I'll go ahead and label this. I drew myself like a free body diagram here. I have 2,400 coming down here. I have 1,500 coming down here. I would immediately go back and identify the moment arms for each of these. The distance between here, that's 30, that has to be 15, because the 2,400 is going to act in the middle. That's 15 feet. And then between here and here, that's going to be 20 feet here. Okay, I make this as the force AY and the moment at A. Okay, my solution is going to be a little bit different than what the solution manual did, but we should get the right answer. So what you want to do here is take a moment. Now, the thing to note, when you take a moment, you have to include this moment here with a cantilevered beam. That's what makes the moment go to 0. Because if you look at it, you have two other forces here that are trying to make this thing rotate clockwise, so you have to have a moment. So all you want to do in this one is sum the forces in the y direction first. You will get FAY minus 2,400 minus 1,500 is equal to 0. FAY minus 3,900 is equal to 0. Okay, this is going to give you 3,900 here for y. Okay, so we know FAY is equal to 3,900. Okay, at this point, go ahead and just take your moment around A. And when you do that, you'll get the summation of moments around A is equal to 0. You're going to get 2,400 times this, which is going to be 15. Let that be 0. Minus 1,500 times 20. And then you have to do this, plus moment around A is equal to 0. Solve for your moment of A. And that's going to give you 2,400 times 15 plus 1,500 times 20. And that's going to give you a moment of 66,000. Or you can say 66 kip feet. That's going back that way. Alright, so that would be your reactions. Okay, very important that you can do this. Again, it's not hard, but just do never ever assume when you have a cantilever beam that the moment there is going to be 0. It's only going to be 0 because you have this moment here that cancels it out. So we have this here, circle this. Alright. Now we want to find the loading at C. Okay, and find the loading at C, what you can do is you can cut the beam right here and look to the left. Just make sure you include all this. So we'll go down here, we'll draw a 5-foot section of the beam like this. We go ahead and we make sure we include everything here. I got 3,900 coming here. You got to include your moment of 66.6 or 66,000 going this way. And I might even, especially on tests, you might want to just list this as 66,000 because you can't mess this up. Now you have to consider the weight of this. This is 80 times 5, that's 400, acting in the middle. Okay. This distance here is going to be 5. This distance 2.5. And this will be our point C. So, and again, I did the 2.5. I shouldn't do that. I should have made that. 2.5 is okay, but I need to label the force. So don't make the mistakes I'm making here. So, now, If we sum our forces in the y direction, we will get 3,900 here minus 400 coming up here, plus FC is equal to 0. FC would equal to, and that's going to give me 3,500 of a force coming up there. That's what. So that has to balance out. So you're going to get. It's going to react this way. Oops. I just show it going down like this. Like that. Okay. Again, the direction isn't that essential. It just means you got shear across here, but it has to go down to balance this out. Now, if you sum the moments around C, you just add moments. Now, when you have this, you do not multiply it by moment arms. So that would be 66,000 minus 3,900 times 5 plus 400 times 2.5 plus the moment at C is equal to 0. And when you do that, you'll get 47,500. So since this is going back this way, it's going to have to go back like that. Okay, and this would be in foot-pounds. Okay, again, if you don't want to go this way, you can just cut the beam here and look to the right. Now to find the reaction at D, if you want to find the reaction at D, the simplest thing is just to do it right here and look to the right. I got a 3-foot section. Just draw yourself a little 3-foot section. You know it's 80 pounds per feet. So 80 times 3, that's going to give me 240 coming down. This distance here would be 1.5. So all you have to do now is to draw what your reactions are going to be. You have a force up here. You have a moment going back this way here. So now you would sum the moments around D. Set that equal to 0. And here you'd get 240 times 1.5. I make that negative, plus the moment at D is equal to 0. And 240 times 1.5 gives me 360 foot-pounds. So it would be reacting this way, like this. However, what's happening here is the beam is going to bend down. So the beam is going to want to bend with 360 going back this way. So if you're doing it for design purposes, the beam's not going to bend up, the beam's going to bend down. And if I was going to answer this in a test, and the question was, what's the internal loading acting at this point, then I would probably just show it like this and show that the beam is bending like this and put 360 foot-pounds. Okay, and then the shear across here would be 360, and it's shearing down across that too. Not 360, I'm sorry. Sorry, I didn't do that yet. Summation of forces in the y direction equals 0. I got minus 240. Plus the force at D is equal to 0. And the force at D would equal to 240 pounds shearing down. Okay, and that's it. That's all you have to do with these type of problems.